Good morning. Can you see the screen? All of you copy down this question. Now we are going for the Parsons reaction turbine, not a D-level, neither a Curtis turbine. It is a Parsons reaction turbine. All of you copy that question. We'll solve. I'll explain how to solve that fast.
So the screen is not yet visible, sir.
Okay, just a minute. Now can you see?
Yes, sir.
Take them. Or I will post one more question that also you take down. We will see this later because there is some condition given. I will take up this later. I'll take up that question later. Okay. I'll give one more question. You copy that. I'll display one more question. We will take up that question also. But first, before we'll go for a complicated one, we'll go for the easiest one. Then I'll move further. Let it be. Be ready with that question also. And one more question I'll post now. Yeah. I hope you have copied this question, no? This question you are done with, I hope. We'll go for this. Take on this. The following data refers to a 50% reaction turbine. The following data refers to a 50% reaction turbine. This means 50% reaction turbine means that it is a Parsons turbine where D is equal to 1.5 meters, where D, diameter of the rotor, is 1.5 meter. Diameter of the rotor is 1.5 meter. And this is, there is some error here. You take this as speed ratio, U by V1, speed ratio. Speed ratio, U by V1, or in the form of symbol phi. Either you take as a symbol phi or a speed ratio. The speed ratio is 0.72. 0.72. And beta 2, outlet blade angle is 20 degree. Copy that question, come back. And the speed of the rotor is 3000 RPM. Determine blade efficiency. Determine the blade efficiency. Determine the blade efficiency. The rotor speed, that is N. The rotor speed, N is already given in RPM. So again, he is asking rotor speed. That means that it is U, meter per second. If the rotor is designed to run at its best theoretical speed, stop. The exit angle is 20 degree. The exit angle is 20 degree. comma, blade efficiency for its best speed is given by blade efficiency for its best speed is given by blade efficiency for its best speed is given by efficiency of blade is equal to 2 cos square alpha 1 divided by 1 plus cos square alpha 1. Okay. Whether I shared the formula sheet for this reaction turbine? Whether I have shared the formula sheet for this reaction turbine?
No, sir. Only impulse turbine.
Impulse and Curtis. Sorry, both impulse. This D level and Curtis I shared, no? Okay. No problem. Here the formulas are not much. I will write down the formulas now. First, I'll write down the formulas, different formulas to be used in this Parsons turbine. Only few are there, not much. Just a minute. Okay. First, I'll write down the formula. These are all the formulas for reaction turbine. The other name for reaction turbine is impulse turbine. Sorry, impulse reaction turbine. It is also called as impulse reaction turbine, 50% turbine, Parsons turbine, or simply reaction turbine. See, there are so many names for the turbines. Either you can call impulse reaction turbine, or simply reaction, or 50% turbine, or Parsons turbine. In this, I hope you know this is the first formula we'll use. U mean, that is mean speed of the rotor is equal to pi d mean n by 60. You observe here d mean because this is very important. Meter per second. Okay, d mean. For example, in some problem he will give diameter 1 and diameter 2. You should not take d1 or d2. Neither d1 and neither of these two. You're supposed to convert the d1 and d2 by. You have to convert this two into dm. You should not directly use d1 and d2. You have to convert this to dm, where dm is equal to d1 plus d2 by 2. That we have to convert and we have to substitute here. Then, second is power developed remains same. Even though it is remains same, I'll write down. Power developed, or it is also called as W dot, is equal to M dot U mean VU1 plus VU2 whole divided by 1000. It will become kilowatts. This is for, I'm talking about the reaction turbine. This formula remains same for either for steam, for impulse or reaction turbine. There is no change. You can observe that. And third one, the one more new formula we are introducing, means we are getting here is, that is M dot. M dot, what is the formula we are used to find out that? M dot is equal to rho A of fluid and velocity of flow. A of flow into velocity of flow. That sometimes he can also ask us 1 by kinematic viscosity multiplied with A is nothing but pi d mean H into, this is not velocity of flow, as per ours it is VA. As per ours we are writing that as VA in terms of kg per second. So here where H is equal to height of the blades. Height of the blades. So all of you write down the formulas. It is almost similar. Just only few steps are included here. And work done as usual. W is equal to E is equal to U VU1 plus VU2. There is no change in this. Then fifth one. Blade efficiency. What is the blade efficiency general formula? Blade efficiency general formula is W by energy available, where W is equal to, in the above step we have written, U VU1 plus VU2 is the W, and energy available at the inlet. There are two terms. One is half into V1 square plus, half into V1 square plus, can anyone tell? While deriving we did VR2 square minus VR1 square by 2. This is the energy available at the inlet. So in some problem he will ask just energy available. There you can write down EA is equal to half into V1 square plus VR2 square minus VR1 square divided by 2. This is the energy available at the inlet. Next, nozzle efficiency as usual. Efficiency of nozzle is equal to half into V1 square divided by delta H dash. Delta H dash. That you already know how to find out delta H dash. From the steam table, you're supposed to take delta H dash, supposed to be taken from the steam table. I hope you know how to take this. Next. Maximum efficiency is equal to 2 cos square alpha 1 divided by 1 plus cos square alpha 1. This is the maximum blade efficiency. And condition for maximum efficiency? Condition for maximum efficiency is what? Speed ratio optimum is equal to cos alpha 1, or it is also called as Umax divided by V1. Next, what is the normal speed rate, normal efficiency? Can you tell? In the yesterday's derivation, you only did. In the last class derivation, you did the normal efficiency. Efficiency of the blade. Say above the 8 point indicates the maximum efficiency of the blade from the reaction turbine. And here I am writing only the blade efficiency. This is not maximum. Cos alpha 1 minus 2 phi square divided by 1 plus 2 speed ratio cos alpha 1 minus. So these are all the formulas we'll come across in this reaction turbine. Can anyone tell what are the different changes or what are the things we have done extra? Here, extra thing is the first one. That is extra. Means compared to impulse turbine, there we used to give the diameter is to give and speed is to give. But here they will give two diameters, D1 and D2. Have to convert that to D mean. That is one extra thing. And this mass flow rate M dot, there we did not use this equation. Here we are using. And this energy available at inlet. Earlier it was EA is equal to half into V1 square for impulse turbine. But for reaction turbine, there is one more term included, that is VR2 minus VR1 square by 2. Then this efficiency is different for impulse and reaction. What is the formula for impulse turbine? Can you tell? Maximum efficiency. We wrote the exam also, internals also, no? And here this is changed. So only these 5 are the equations where it is differed compared to the impulse turbine. Are you getting? Hello?
Yes, sir.
Okay. Those are the changes what we are seeing in reaction turbine compared to impulse turbine. This you all know because efficiency there it will be different, here it will be different. Energy available there is different, here it is different. M dot, this is general equation, that is M into Q, rho into Q. Q is A into velocity, area into velocity. Area is pi d mean H into VA. So anyhow VA, you can ask what is VA, whether I should use VA1 or VA2. Use VA because VA, the length of VA is common for reaction turbine, no? So there is no issue. You can use this. Either VA1 or VA2, it will be same. Shall I remove this?
One minute, sir.
If it is done, please let me know. Okay, once it is completed, let me know.
So the equation for M dot, it is 1 by rho or V, sir.
This is kinematic. See, rho can be rewritten as, here it is density.
Yes, sir.
1 by Can you tell what is this?
V.
Via.
It looks like V, sir.
Can anyone tell? Huh? Don't know.
Mu.
This is viscosity.
Mu, sir. Mu.
So let me, you inform me once it is done. Okay, I'll write down that also. So for your reference, I'm writing this and have a look at this. Okay. Chinmay. Chinmay, are you there? Hello, Chinmay. Chinmay. So you can write mu by kinematic viscosity, or if I write like this, it will become specific volume because rho is density is kg per meter cube. In some problem, he'll give the specific volume. Okay, I hope you have completed this. I'll go for the problem now. This is the formula for whether it is done or not. Somebody speak, no?
Yes, sir. Done. Sir.
Okay.
Done, sir.
Now I'll go for the next sheet. Okay. So now I'll write on the data with respect to the given question. All of you open the question there. What he has given? The stage refers to 50% turbine. So all of you write down this heading, whether it is a Curtis turbine, D level or 50%, because the formulas are different for all. So, and the reaction turbine diameter is having D is equal to 1.5 meters. See here he has not given D1 and D2. Let me take this D itself as DM. And the speed ratio is equal to U by V1 is 0.72. And beta 2 is equal to 20 degree. Speed of the rotor N is equal to 3000 RPM. Find the blade efficiency. Blade efficiency is how much? Percentage increase in the blade efficiency if it is used using provided if we use max. How much? Next, what is asking? Exit angle of the steam alpha 2. Exit angle of the steam is 20 degree. The blade efficiency of the piston. Okay, he has given to you. It will be easy for you so that he has given the blade efficiency. Maximum blade efficiency is this. If he has not given also, you should use this. So this is the given data, correct? Those are all the data given. Now what I will do is, I will go with what is this? Can anyone tell what is the standard for impulse turbine? For impulse reaction turbine, what are all the standards? Standard is V1 is equal to VR2, V2 is equal to VR1, alpha 1 is equal to beta 2, alpha 2 is equal to beta 1. Then usually it will be VA1 will be equal to VA2. This is a generalized term what we know while solving the problem. Keep this in mind. Whether it is applicable for this problem or not, we will see. First, you please keep this in mind, okay? And then we'll proceed further. Whether it is given alpha 2, just a minute, I'll check out. Why alpha 2 is given? It should not be given. Blade efficiency. The exit angle is 20 degree. See here something is missing. Exit angle for the blade it is, not exit angle of the steam. Just a minute, I'm checking it. We'll see. I think somewhere he has done something in this. Data is missing, I guess, because in your beta 2 is given. We'll see how to do. First, we'll go with the velocity triangle. Here, as usual, we go for the scale ratio. Before going for the scale ratio, you find out D mean. First step, you find out U mean is equal to pi D mean N by 60. So you know pi D mean is 1.5, speed is 3000 divided by 60. So somebody tell me the value of U mean in meters per second. What is
Sir,
mean?
235.6 meter per second.
235.6 meters per second. That is the U mean. Then I'll go for the second thing is, I'll go to find out V1. So how to find out V1? With the help of speed ratio. Speed ratio is equal to U by V1. Therefore, V1 is equal to, can you tell how much it is? U is nothing but U mean.
227.2.
235.6 by speed ratio. How much it is?
327.2
meters per second. We got V1 also. So here we got V1 and we got U. Clear? So now you go for the third one, that is drawing a velocity triangle. To draw velocity triangle, we want scale ratio. What is the scale ratio supposed to take in until now? Again, you see as U mean you see, and or you can also see V, anyone. So I told it should not exceed 4 centimeter. How much it will be? What is the scale ratio? Anyone? Or simply shall I take my scale ratio? I'll take my scale ratio. 50 meters per second is equal to 1 centimeter. I'll take like this. If it is 50 meters per second, we'll take it as 1 centimeter. Then I'll draw U. To draw U, I will draw the horizontal line first. What should be the length of horizontal line as per the scale ratio? 235.6 by. It's supposed to be 4.7. Yeah. You did not told I take this scale ratio. We'll see. I think probably you can accommodate here. No issue. So I'll take the U equal to 4.71 centimeters. Or you can take any scale ratio. There is no rule that you're supposed to take this. And this dimension is called as M. So you practice one thing. In the reaction turbine, you try to write down UM. Instead of U, you write UM. That's all. And what is the line I supposed to start from here to here? If I draw the line, it's supposed to be alpha 1. Whether alpha 1 is given in the question? No, alpha 1 is not given. But
Beta 2. Beta 2 is
beta 2 is equal to alpha 1. So that beta 2 is 20 degree. We will from this point, I will draw 20 degree.
So this triangle should be taken vertically or horizontally?
Which one? Yeah, you can take horizontally, no problem. Like the same as D-level turbine, you can accommodate.
Okay, sir.
There I am showing, no, there like that only we take, no issue. So here this will be V1. V1 we got, what should be the length of V1 as per the scale ratio? To 325, 327.25. As per my scale ratio, it is 6 centimeter only. It is just a 6 centimeter. So I have drawn 6 centimeter line and I have joined the arm. Once you've done this, can you tell what is the next step? Simply drop down the vertical line. Write this as VA1. Join this. Complete this figure. So this is VR1. And from here to here it is VU1. So that this is all. So this is called alpha 1 and this is called beta 1. So from this figure, you find out beta 1 first. Here additional data given, that is data somewhere he has done mistake. That alpha 2 should not be given. This is supposed to not be given. Or that is some other meaning. It is nothing but an exit blade angle like this. The printing mistake it is. Don't worry about that. Because we know for a Parsons reaction turbine, beta 1 will be also equal to alpha 2, right? So no need to give the alpha 2 there. He has given by mistake beta 2 must be given. He has given alpha 2 by mistake. Can you complete the outlet angle? So to complete the outlet, I am supposed to start from here. What is the angle I am supposed to take now? Can you tell? What is the angle I am supposed to take here? I am supposed to get here beta 2. Where beta 2 is equal to what? Beta 2 is equal to?
alpha 1.
Alpha 1, right? Yes. That is equal to how much?
20 degrees. 20
degrees. And length of this should be how much? Even though this is VR2, length of the VR2 should be equal to V1. VR2 should be equal to V1. So no need to worry about CB here. CB will not come into picture here. V1 is equal to VR2 will come. Then join this, drop a vertical line, complete this. So this is called what? Alpha 2, where alpha 2 is equal to beta 1. And this is called V2. This is called VA2. And the gap between this and this is considered as VU2. Understood how easy it is? Here there is no question of CB. Just if you know how to draw the inlet triangle, outlet is replica, mirror image of that. Have you done this till here? Try to draw to the actual scale. Try to draw to the actual scale. In the question, you please strike off that data. It is alpha 2 is 20 degree. I hope there is a printing mistake, or you write down Exit blade angle. Exit blade angle is 20 degree. That's okay. If you write exit blade angle. Have you done this?
One second, sir. One second.
Say all of you try to draw to the actual scale. I may ask a few questions to upload as an assignment at the end of the module, at the end of this module. Okay, be ready with the questions along with the solution to the actual scale. If you ask the same question, you can upload that as an assignment. Understanding?
Yes, sir.
So write down in the prepared sheet properly to the actual scale. Be ready with for everything. As a notes also, it will be helpful. Okay, I hope you have completed. I'll go for the next further step. What he is asking to find out in the question? He is asking you to find out. So now you first put a table for V1 U. V1 will be equal to VR2. V2 will be equal to VR1. Alpha 1 will be equal to beta 2. Alpha 2 will be equal to beta 1. Then VA1 will be equal to VA2. Then what else is left out? Beta VRV. VU1 is how much? VU2 is how much? You put this as a table. Here, meters per second, centimeter. However, it's convenient for you, try to put the table. Fill up this table. Can anyone tell the answer? How much it will be?
VU1 is 305 meter per second, sir.
305. As per the scale?
As per the scale, 6.1 second.
Others also should reply.
6.1 as per the scale, sir.
6.1. And others, what are the other values? Huh?
So VR1 is 135 meter per second.
135 meter per second. How much as per the scale?
2.7 centimeters.
2.7.
Yes, sir.
Others? Other values also you tell. Alpha 2 is how much? Beta 1, have you calculated how much you got?
Around 57 degrees.
7?
57 degrees.
57. Here also write 57. What about VA1 and VA2? Somebody calculated? And VU2. So finally, your aim should be to fill in this. Now we'll go for the next step because this you can get from the figure. What he is asking to find out? He is asking you to find out. First thing is blade efficiency. So we'll go for that as a third step. I'll take out and then I'll find blade efficiency. What is the formula for the blade efficiency? Generally, the formula for the blade efficiency will be equal to W by energy available. Either you can separately find out W and energy available separately, or you can find out work done divided by energy available at inlet. You can write like this. So what is work done and energy available separately? U, I'll write U mean VU1 plus VU2 is the work done divided by energy available is half into V1 square plus VR2 square minus VR1 square divided by 2. Multiplied with 100, you'll get efficiency of the blade. Can anyone tell what is the blade efficiency? In percentage?
Calculating, sir.
No, okay. Calculate and tell me the answer. So either you can do separately, work done separately, energy available at the inlet separately, substitute in blade efficiency. Hello. Answers?
Sir, is it 90%, sir? Blade efficiency.
Yeah,
Blade
whatever you got to tell me, 90 point.
90.3, sir. Approximately.
Okay. And what about maximum blade efficiency?
That I'm calculating.
Others also calculate and tell the answer.
Maximum blade efficiency 93.7, sir.
It has to get more than that. Okay. So if you substitute here and simplify, how much you get? Percentage increase. This will lead to an answer of how much percentage increase.
%3.7%.
Very good.
3.76.
76, huh? See, if it is a maximum,
3.76.
okay. If it is maximum, I will get more efficiency. That is 93.7%. If it is simply, if I use a blade efficiency, I'll get 90.3. So this kind of question can ask in D level also. Percentage increase in the blade efficiency. So you have to do first blade efficiency, and also you have to find out the maximum blade efficiency. Using this equation, you can find out the percentage increase in the blade efficiency if I use a maximum. I'll post one more question. You try to solve that. We'll see. Can I take up that as an assignment for today's class? I'll post one more regarding the Parsons turbine. Try to solve and submit. We'll see how you are going to analyze this problem. This is again, see the problem I already posted in a WhatsApp group. I'll give that as a quiz today. You write down that in a sheet. Write the question also and then try to solve. Write the question and then try to solve. I'll stop sharing the screen now. Today I have posted one. Just now I have posted one more question regarding that. Also, I'll project and I'll explain what. See here, can you see? A Parsons turbine, the axial velocity of the flow of the steam is 0.5 times the mean velocity. That means what? Can you tell? Axial velocity of the flow of the steam. It is VA. VA is equal to 0.5 times the mean blade speed. You mean this is the new thing for you. After giving U, VA is given in terms of U. You can do that. VA is equal to 0.5 times of U. Next, the outlet angle of the blade is 20 degree. That is beta 2 is 20 degree. The outlet angle of the blade is 20 degree. You know, for the Parsons turbine, if beta 2 is 20 degree, alpha 1 is also 20 degree. Next, the diameter of the blade ring is 1.3 meter. That is d mean. And the rotational speed is 3000 rpm. So, with the help of these two, I can find out U. Then determine the inlet blade angle, power developed of the steam for the steam flow rate of 65 kg per second. And the isentropic enthalpy drop if the stage efficiency is 80%. He himself has given the stage efficiency as 80%. Can you try to solve? Or shall I give a hint of formulas? I hope you will be having doubt in only this. The isentropic enthalpy drop. Whether I given today's formulas, isentropic enthalpy drop, whether I given? No, I have not given. You write down that. Isentropic enthalpy drop. This formula for isentropic enthalpy drop, or it is also called as theoretical enthalpy drop. This isentropic enthalpy drop, or also called as theoretical enthalpy drop, is equal to W divided by stage efficiency. W by stage efficiency. W by stage efficiency in kilojoules per kg. See, this is somewhat tricky. You try to find it, because he has nowhere given the speed ratio. He has nowhere given V1, but he has given in terms of VA1 is equal to 0.5 times of U. You have to find out and upload this as a quiz. Write down the question also. While uploading today, you write down the question and then upload. Is it clear?
Yes, sure.
All of you give your reverse number, type your reverse number, be in the class. Next faculty will come and join me. Only once you type UAS number. Everyone is done? Only 43 have given. Do it fast. 7. Still 3 more. Those who have not typed your number, you can type here. So I'll stop recording the class now. Be in class. Next faculty will come and join. Okay. And then today's quiz. I hope you understood what is the today's quiz. Zahir is saying. Okay.
Yes, sir.
While writing a today's quiz, you write down the question also. Okay. I'll stop the meeting now.